Okay, so welcome everybody to the afternoon session of today. And our first speaker will be Sergey Neshveyev from Oslo. And I think he will talk about Kohno-Drinfeld type theorem for symmetric spaces. So please.
Thank you. I would like to thank the organizers for the invitation. And it's a pity that I kind of was not able to come to Rome in person. Hopefully next time. So I will talk on this Kohno-Drinfeld type theorem for symmetric spaces. It's a joint work with Kenny de Kommer, Vartuset, and Makoto Yamashita. So let me start first by reminding what the Kohno-Drinfeld theorem is. So we start with a complex simple Lie algebra G, and we consider the Drinfeld G-mod deformation UHG of universal enveloping algebra G. And since we're in the simple case as algebras, we can identify this algebra, quantized universal algebra, simply with the algebra of formal power series with coefficients in G. And inside this algebra, there is a universal R matrix, so precisely an element in the second power of this algebra, and it is a solution of the Yang-Baxter equation. So since if we have such a solution, then we can produce representations of the Bragg group. So more precisely, we take any finite dimensional G modulo V, and then we can define a representation of the Bragg group Bn on n strands on the nth tensor power of V. We have to extend the coefficients in the formal power series. So more precisely, the ith generator of the Bragg group acts on the ith and I plus first factors of this tensor product, and the action is by this R matrix and the flip map. On the other hand, there is a different construction of representations of Bragg groups on such modulus. So namely coming from Knizhnik homological equations. So those are defined as follows. So we start with a, again, suitably normalized invariant symmetric tensor T. It's unique up to scalar, but we have to normalize properly for things to work. And so we consider the configuration of points yn. So these are all points in the complex space Cn, such that all coordinates are different. And then the Knizhnik homological equations are just Kz equations for every n. This is a system of differential equations of this form. So where this Tij is this tensor T acting on the factors I and j. And the equations are viewed as equations on Rn with values in this nth tensor power of V, with and tensor with formal power series and page. So this system of equations is consistent. So locally you have a unique solution for any initial point, so for any initial value. But then when you start prolonging these solutions along different curves, then the result can depend on the curve, not on the just the first point and the end point. So in other words, you get a representation of the fundamental group of In, but in fact, because everything is symmetric, we can consider divide Yn by symmetric group. And the fundamental group of this space is exactly the Bragg group. And so as a result, we get a monodromy representation of the Bragg group on the same space. So we have for every G modulo V, we have two representations, one coming from this universal I matrices, the other coming from monodromy of Knizhnik homological equation. And the theorem of Kohno from 1980s says that for any V and N, these two representations are equivalent. So soon after Kohno proved it, Drinfeld found a kind of deeper explanation of why it is true. So the proof of Kohno was based just on analysis of sort of I matrices and with Kz equations. But Drinfeld showed that there is a deeper common structure behind these two representations. So at the first glance, they look at something coming from completely different worlds, one from I matrices, another from this Kz equation. But in fact, he showed that Kz equations actually also define you some sort of deformation of universal enveloping algebra, suitably understood. And then from this point of view, both representations are of similar type. And what the true result says that these two deformations are equivalent. So let me formulate this precisely. So because this is what we're going to use during the entire talk. So recall how it is done. So the most important element here is this Drinfeld KZ associator. And it is defined as follows. So we consider just the KZ3 equation. So we consider this equation that just when n equals 3. And so we consider monodromy of this equation from the asymptotic zone where Z1 minus Z2 is much smaller than Z1 minus Z3 to the asymptotic zone where Z2 minus Z3 is much smaller than Z1 and Z3. So more precisely, when you kind of move to infinities, you have, if you just literally consider monodromy, there are some oscillating factors which are always present, and you have to properly normalize such things to make sense. So rigorously, what one does is the following. So we can consider the change of variable. So we have these equations in 3 variables. We can consider change of variables of this form. So this is kind of the factor which will always be present in the solutions, and this is the factor we want to get rid of. But in terms of W, the equation then KZ3 equation then reduced just into one equation with 2 singularities, 0 and 1. And we consider the solutions of these equations on the interval 0, 1, those values in the endomorphism of V. Again, extended to form of our series. So the solution is uniquely determined by initial conditions on any point in interval 0, 1, but at the singular points at x equals 0 and x equals 1, we can normalize them sort of differently and then compare how these 2 solutions are related. So in other words, there are 2 solutions, G1 and G0 and G1. So G0 is sort of normalized at 0 in such a way that if you take the following function, then this function is extends to a homomorphic function with value 1 at 0. And we consider a solution G1 such that G1 1 minus x multiplied by this factor. So this function extends to the homomorphic functions. And then you do this again with value 1 and 0. And so, but they are still related just by, sort of constant operator. And this is operator, this is what is called the Drinfeld KZ associator. So we can do it on every representation V, and as a result, we can view this element as an element of this triple tensor product of the universal enveloping algebra. And this element defines, it satisfies nice properties, namely, it satisfies the pentagon relation. So you can view this operator, sort of operator shifting brackets from V1, V2 into V2, V3. And then if you have 4 such products, and you have all brackets sort of shifted to the left, and you want to shift it to the right using this operator, there are 2 ways of doing this. And the claim is that these 2 ways coincide. And what it means is that in fact, we have a new tensor category structure on the representation category of our Lie algebra G, where new associativity morphisms are just sort of the obvious one, but then modified by action of this element. And then the result of Drinfeld says that, okay, so we have 2 tensor categories. On the one side, we have category of modulus of this quantized universal enveloping algebra, which is braided tensor category with braiding defined by universal M matrix. On the other hand, we have a Drinfeld category, where associativity morphisms are given by this KZ associator, and the braiding is very simple. It has just this form. So, and they claim that these 2 braided categories are the same. And this implies Kohno-Drinfeld because then these 2 types of representation, they simply come from 2 representations defined by braidings in these 2 categories. Okay, so what? So this is the original theorem of Kohno and Drinfeld, and the talk is about some sort of generalization of not generalization, but some analog of this result. So namely, instead of usual braid groups, we'll consider this type B braid groups. So recall these are defined as follows. So braid group of type Bn. So it has n generators. So you have the generator C1, sigma, and -1. And special generator ρ1 satisfying the following relation. So the relations for sigma are the usual relations in the braid groups. But relations for this generator ρ1 as follows. So they compute the generators sigma I as soon as I is larger than 1. But for the first generator, you have the following identity. And this group can be considered as a subgroup of the usual braid group on n+1 strands. Namely, what you do for all these generators, sigma 1, sigma n1, are the usual generators of the braid group, but starting from sort of the second strand. So the first strand plays a particular role. But if you start looking at the second and so on strands, then on those strands, these generators are the usual generators of the braid group corresponding to these braids. While for sort of the first strand, so on the first two strands, you have this generator ρ1, and it corresponds to a picture like this. So then, say these relations are kind of media because ρ1 involves only the first two strands, while all the sigma i's will start with strands number 3 and so on. So they're of course complete. But this relation has so in pictorial form. This is the proof of this relation. So the relation looks as follows, and it's true because you can sort of pass this strain under this one. So if you do passing it sort of through here, then you'll get exactly this one. And this relation is closely related, or it's basically so-called the reflection equation. What we get if we have a solution of reflection equation, then we can get a representation of this type B braid group. So more precisely, if you have a solution, so it's this A matrix, a solution of the Yang-Baxter equation. So we have then a representation of the usual braid group for generators starting from sigma 1 to sigma n minus 1, say. But if we want a representation of this type B braid group, we have to find sort of a solution of this relation. And for this would be enough to find an element k acting on V such that the following relation is satisfied. So this is exactly this relation where this k acts on the very first factor. So the first factor, the first strand corresponds to complex numbers, just trivial one-dimensional representation, and this k acts only on the first strand. So if you have a solution of this reflection equation, then you get a representation of this type B braid group. And the reflection equation appeared already also in the 1980s in the work of Cherednik on quantum scattering methods on the half line. So this sort of this operator corresponding to this braid, it's sort of operator describing bouncing of a particle, say, of a wall. And so there has been a lot of interest in finding solutions of this equation. And what were one of the questions in view of this Kohno-Drinfeld theorem can be as follows. So is there some sort of quantization problem which produces you solutions of the reflection equation, similarly to how quantization of universal enveloping algebras produces this universal R matrices, which are solution of the Yang-Baxter equation. And then, if you have two ways of kind of doing this, can we compare such things? And I will give an answer to these questions in a particular case of symmetric spaces. But I'll explain how this is related to symmetric spaces and then homogeneous spaces more generally. Okay, so we want to formulate this sort of quantization problem, which is related to this reflection equation. But let me first just formulate more precisely what the quantized universal enveloping algebra is and what exactly it quantizes. So let us consider the simply connected complex Lie group with our fixed Lie algebra G. We fix its compact form. We fix a maximal torus in this compact form, and we choose these Cartan-Weil generators. And the Poisson, there is standard Sklenin Poisson structure on our compact group U, defined by the following formula, where R is given by this formula. And here LL means that you act on the left by right invariant vector fields, and RR means that you act on the right by left invariant vector fields. And then the universal enveloping algebra quantized universal enveloping algebra of Drinfeld-Jimba, it quantizes sort of this Poisson structure. So more precisely, I call that this is algebra with generators, which are similarly to Cartan case, to classical case. So you have the generators corresponding to Cartan elements, and you have this generators Fi corresponding to X alpha I, Y alpha I for simple roots alpha I. So the relations are, some of them are very similar to classical case. So these two relations are exactly the same as in the classical case, and this is different. Yeah. So instead of HI, you get this kind of expression. Plus, you have more complicated relations. That's quantum C relations, but I will not write them. And what you get is this algebra with a star structure. The star structure, I will not say much, but it will play an important role in what we do, because this is what allows us to think of everything as coming from a compact space rather than a complex space, and which simplifies certain things. So the coproduct is given by these formulas, and that it quantizes this, so that the fact that you really get a quantization of your Poisson-Lie group is reflected by the properties that this coproduct coincides with the classical one, modulo H. While if you look at sort of semi-classical limits, then you have identity of this form. So if you take the coproduct and take the coproduct with a flip, then you get this co-bracket H modulo H squared. Right? So, but now, so the question which we're interested in is, people are interested in is quantization not of just groups, but of homogeneous spaces. Precisely, if you what one means by this, so if we have a homogeneous space of the group U, and we look at Poisson brackets on this space, and such Poisson brackets such that the action map is a Poisson map. And then equivariant quantization problem is asks whether we can quantize algebra functions on this manifold, or maybe some regular functions, nice class of functions, in sort of an equivariant way. So in other words, you want something which is a modular algebra over this quantized universal envelope algebra of G. This problem has been solved in a number of cases, but there is no general solution for this. The simplest case, which was kind of clear from the start already, from the in the 80s, is when this stabilizer group K is a Poisson-Lie subgroup, which means that if you take this co-bracket, then this co-bracket, when you restrict it to Lie subalgebra, still preserves sort of Lie subalgebra, that it maps this Lie algebra of K into Lie algebra of K times the Lie algebra of K. And in this case, you really get a quantization of a subgroup, and so you have quantum group, quantum subgroup, and you can consider homogeneous space defined in the obvious way. But unfortunately, actually, there are not many Poisson-Lie subgroups, so you can completely classify them. It's more or less the same numbers, the number of parabolic subgroups in your group. So the class of all Poisson homogeneous spaces is much larger than the ones corresponding to Poisson-Lie subgroups. And some of them have also been quantized. Probably the most famous example is, the easiest example is the Podlish sphere. So with the Podlish sphere, it is a homogeneous space of SU2. You can identify it with SU2 modulo the torus. And on this space, you have the following Poisson structures. So all Poisson structures making it into Poisson homogeneous space over SU2 are given by the following formula. So they're parameterized by complex numbers, and here is the whole family of them. And those have been explicitly quantized. So at the level of, say, function algebras, these are algebras satisfying this. So with 3 generators and several relations. But in fact, in this case, it's more convenient to look sort of on the dual side. So instead of considering subalgebra of function algebra on the quantum group, or just an abstract algebra in which you have action of SUP2, it's convenient to consider sort of the dual subspace of the quantized universal enveloping algebra. And this is even easier to describe. So it shows out that these coideals, so coideals in this quantized universal enveloping algebra are just given by, they're generated just by one element, so element of this form. So in all three cases, you see that there are some complex parameters. So you have sort of one parameter family of Poisson structures. Here you have one parameter family of algebras, and here there is one parameter family of coideals. Here there is some correspondence, explicit correspondence between all these parameters, but I didn't write it down. So this is kind of the easiest example, and this is example which we want to generalize, and which it has been generalized. So namely, the Porgic sphere is the simplest example of a symmetric space. And this is the class of spaces we're interested in. So more precisely, what we're going to consider, and formally this is called a irreducible compact symmetric space of type 1. So this is a homogeneous space of the form U mod K, where K is just a fixed point for some non-trivial involutive automorphism of U. So on this space, it turns out that there is always, so there is some canonical Poisson structure. So namely, we take the same R matrix which we use to define the Poisson structure on the Lie group and act only on the left. So on the right, it doesn't immediately make sense, but on the left, it makes sense. And it turns out that this is a well-defined Poisson structure, and this gives you a Poisson space. Furthermore, already at this point, one sees kind of this dichotomy, which one often has for symmetric spaces. So there is a particularly nice class of symmetric spaces, so-called Hermitian symmetric spaces. And if you are not in this Hermitian case, it turns out that this is the only Poisson structure. But if you are in the Hermitian case, there are more. And from now on, I will only consider these Hermitian symmetric spaces. And the reason is kind of the following: that on the one hand, this is more complicated and more interesting, exactly because you have many Poisson structures, or as we will see, many others related sort of non-uniqueness type of statements. But at the same time, the formulations also become somewhat better. So the case of non-Hermitian space, it's easier, but at the same time a bit more awkward to formulate. So I will just abandon it, and we'll consider only Hermitian spaces. So what are the so first of all, what is a Hermitian symmetric space? So given such symmetric space, you can characterize this Hermitian symmetric spaces in many different ways, in purely geometric or in Lie algebraic. So here are 5 different ways of formulating this. So geometrically, this means that this homogeneous space has an invariant Hermitian structure, which explains the name. Another way of saying is that this symmetric space is isomorphic to a coadjoint orbit of U. So it's just the orbit of an element in the dual of the Lie algebra. At the Lie algebra level, one can say the following: that so this fixed point, so the fixed points under our involution, this Lie algebra of K, so it's always a reductive Lie algebra, but it turns out that exactly in the Hermitian case, it's not semi-simple. So it has a non-trivial center, and probably this center is one-dimensional. And this is what makes life more complicated. So in the non-Hermitian case, the center is trivial, your subalgebra is semi-simple, and this simplifies many things. Another way is to say that that on the complement in our Lie algebra view of this Lie algebra of K, you have a unique, you have a K-invariant complex structure. So this is closely related to 1. And another property, which is kind of implicitly will be very important for everything what follows, is that you consider skew-symmetric tensors on M, which are invariant under K, then this space is non-zero and one-dimensional. So if you deal with Hermitian symmetric spaces, then we have sort of a pencil of Poisson structures compatible with action of your Poisson Lie group. Namely, we can take this one which I defined here, this Donin-Schneider structure, and you can take the Kirillov constant Fourier form on the coadjoint orbit and just multiply it by any number. So in this way, you can get all possible Poisson structures which make it a Poisson homogeneous space. So as a result, you should expect that if you manage to quantize it, then you have one more parameter of quantization corresponding to this extra parameter x. So similarly to the case of Podlish sphere, then we have a one parameter family of spheres. Okay, to be concrete, here is a complete list of such symmetric pairs at the Lie algebra level. Okay. So I separated them into blocks, and we will not see very well maybe the reason why it is done, but in fact I could have separated into spaces with somewhat different properties. And the most studied and most well-known is this probably A3 case, where you just consider a special unitary group, and inside of it you have two unitary groups, and you take a special subgroup of groups with determinant 1. So the sphere case corresponds to just this case where P is equal to 1. So it turns out that all of this have been quantized, although without analysis of Poisson structure, just sort of as at the level of kind of generators and without clarifying derivation with Poisson structures. So that was started in the 90s, and in full generality, it was done by Letzter, and later Kolb streamlined these presentations and extended even to the Kant-Spudi case. So briefly, what happens is it's as follows. So you can classify automorphisms. So we have invalidity automorphism for our Lie algebra, and they can be classified by Satake diagrams. In combinatorial forms, it just means pairs X Tor, where X is a subset of simple roots and Tor is an involution satisfying with certain properties. And up to conjugacy, it turns out that any involution then has the following form. So where omega is this particular automorphism, Chevalier automorphism, Tor is just automorphism coming from the automorphism of the Dynkin diagram, so just permuting the generators. And then you have conjugation by a certain element, where Z is just an element of the torus, essentially uniquely determined just to make this an involution. Not every element will give you an involution. And sort of the most complicated part is this part, where you conjugate by a particular element which corresponds to the longest element in the while group generated by reflections corresponding to roots in the set X. And in this form, then the fixed point algebra, or more precisely, is complexification can be described as follows. So this is a subalgebra generated by all these generators corresponding to roots in X, plus all elements of this form, where you take roots not in X. And in this description, this is what Letzter did. In this description, one can generalize the entire construction to the quantum case. But the formulas become sort of complicated. So the most complicated part is this adjoined by this element corresponding to the longest, this element in the group corresponding to the longest element in this while group WX. And this corresponds to some Lustig-Braid automorphisms, and they have quite complicated formulas. So basically, the larger the set X is, the more complicated this automorphism is. But in a compact sort of form, if you just write it as some known automorphism, that explicitly this Letzter-Kolb coideals are defined as follows. So similarly to the classical case, so these are subalgebra of this quantized universal enveloping algebra generated by, again, all elements corresponding to the simple roots in X, all elements in the torus fixed by sigma, and these generators. So these generators are generalization of these generators we saw in the Polish sphere case. But this is much easier because here we don't have these listic automorphisms. But here, the full expression is really complicated if the set X is relatively large. So you get tons of these subalgebras, and in fact, it's not clear at all what they quantize and why it's kind of a reasonable one. So it turns out, and this is what we particularly did in our work, that we show that most of these co-ideals actually do not correspond to something you probably want to consider. But if you require compatibility with the star structure, and this should sort of correspond to quantization of really compact space, then you have tons of the restrictions on all of these parameters. And in fact, there are always, in the simplest case, there is always either one parameter which you can take, or you have two related parameters which you can take. So you really have one parameter family of co-ideals, which is kind of what you want to see, because if you remember, we have one parameter family of Poisson structures. Yeah, so to give an example, so again, let us consider this A3 case. So in A3 case, so you have the standard Drinfeld diagram corresponding to A of type A-1. So what corresponds to this pair? So you have two cases where this P is either n-half, so when n is even, or when n is odd. So in this case, the set X is empty, and your involution of the Drinfeld diagram just sort of flips these roots. In this case, the set X can still be empty, depending where P is, or can be non-empty. And you have this in involution again doing the same thing. So the difference between this and this case is that here you have a wide vertex, not in X, which doesn't go anywhere, and here you don't have such a vertex. And it turns out that in the first case, there is just one parameter you can take. So to define all these deformations, this parameter SP, while all these parameters C are fixed. And in the second case, you have these two parameters, but they have to be related. So you can choose one of them, but the next one is fixed by this identity. So this describes sort of, if we compare with the situation for the Drinfeld-Kohno theorem, so we have two approaches to quantization. So one was through explicit formulas for quantized universal and open algebras and R matrices. And the second was through these KZ equations. And here, what we have done is a description on the in the quantized on the quantized universal and the open side. And so the next we need a construction similar to KZ equations, and this can be described as follows. So again, yeah, maybe I should stress that these co-ideals. So the co-ideals mean so you have these co-ideals means that these are not Hopf subalgebras. So if you apply co-multiplication here, you end up in tensor product of this subalgebra and this algebra. So this is what co-ideal means. So then at the categorical level, so we consider the category of G sigma modulus, but again, we should not expect to quantize it as sort of as a tensor category, because that would rather correspond to quantum subgroups, and we saw that we don't get the quantum subgroups, we got only co-ideals. So the right point of view turns out to be is to view this category as a category of as a modular category of the category of G modulus. So in other words, the structure is that you have your category of G sigma modulus, and you allow to multiply on the right by a G modulo. And obviously, this way you can get a G sigma modulus. You simply can view this tensor product as a representation of G sigma. Okay? This is your modular category structure. So, and we're going to deform or quantize this category really as a category, as a modular category. And what we aim to obtain is a modular category over the Drinfeld category. So what you need for this is, again, some sort of associativity morphisms. So you have an elements in your modular category, which you want to multiply on the right by elements in your tensor category. But you have to be able to distribute brackets. So you have to be able to go from X tensor V tensor W into X tensor V tensor W. And again, if you do it, if you have all brackets on the left and want to move all brackets on the right, there are two ways of doing this. So you need this element psi doing this, sort of making this diagram commutative. So as soon as you have such sort of natural elements, you get some sort of deformation of your modular category of G sigma modules. And it turns out that such an element again can be constructed from KZ type equations, and that was done by Enriquez and then by Enriquez Ettinghoff in the particular case we're interested in. And you can, again, if you remember that Drinfeld associator is defined as some sort of normalized monodromy of KZ equations. Here, this element will be defined as a normalized monodromy of two so-called two cyclotomic equations. So how do they look like? So where in the Hermitian case, remember that this case corresponds to the assumption that the center of this fixed point Lie algebra K is one-dimensional. So we have this unique element up to scalar, and we normalize it in this way. And then we define the following elements. So we consider this canonical tensor, which we used also to define KZ equations. And we consider components in K tensor K and in M tensor M. Remember that M is the complement of K. And we consider the following elements defined in terms of, where CK is the Casimir element, and this TK, TM are these components of our canonical tensor T. So this depends on the choice of parameter S, which again, we need in the kind of Hermitian case because we want to quantize not just one Poisson structure, but a family of Poisson structures. So if you have such elements, then I will not write the kind of full form of two cyclotomic equations, but I will just write this modified equation, which is enough to define this associator. So the equation looks as follows. So compared to the KZ equation, if you remember, the new thing is that you get three summands. So you have extra summands with singularity at -1. And this explains the name two cyclotomic. So you have this, in addition to 0, you have two singularities at 1 and -1. And you have these elements A, which are kind of similar to T, but a little bit more complicated than just T, which we have in the usual Kohno-Drinfeld equation. And then in a similar way as for Drinfeld associator, we can consider normalized monodromy from 0 to 1. And it turns out that this is a well-defined element, at least under some restrictions. And it is indeed a solution of this equation. So it satisfies this pentagon relation. So we indeed get a deformed modular category. Okay. So there is some also technical detail that, in fact, we wanted an element like really here, but if we're careful, we will see that possibly this monodromy is not quite here, but in a certain completion of this algebra. But it does not matter. For modular categories are still well defined because we always act only on some finite dimensional spaces. Okay, so this is really a minor point. Okay, so we have this now. Almost have these two sides of the story. We have sort of Q side with lesser co-ideals, and we have KZ side with modular categories described in terms of Kohno-Drinfeld equations. But yeah, in both cases, the categories are actually so-called ribbon-braided modular categories. So similarly, again, to the original case of Drinfeld, we don't just have tensor category, we have braiding of the categories. And here we have additional structure which explains why this type B braid group appears. So yeah, so you need something corresponding to that braid defining the type B braid group. So more precisely, so this is a notion which was introduced by Brashear a few years ago, and as follows. So what is a ribbon braided modular category? So you have a modular category. So you have some objects in the category, and you allow tensoring them on the right. So right modular category by some tensor category. And you require that there exists a natural morphism from X tensor U into X tensor U, which you depict as in the same way as we depicted this extra generated in the type B braid group. And there are two relations which kind of imply that relations we had in the braid group. So one is the octagon relation, which looks as follows. So you can sort of move V around in two ways, either immediately sort of around X in U, or you can first flip it, then move around X, and then again flip. And these two ways should coincide. But the situation is actually a bit even better because you have so-called ribbon braid. And to distinguish it from the usual braid, it is denoted by this symbol. So you kind of have an extra term here to indicate that you really have a better structure. And then you have this ribbon twist equation. So it just says that either you can go around X sort of immediately using UV, or you can do it sort of one by one. So first for U, then for V. And this extra braided. Okay, and it turns out that on both sides you actually have the structure of ribbon braided modular categories. So in the case of on the Q side, in the case of Lester, Pope, Koadios, this was done by Pope based on earlier work of Pope and Balagovich. On the KZ side, that was basically done by Enriquez, although Enriquez's work is like from 15 years ago when the notion of braided modular category did not really exist. So it's not exactly what he stated, but it's basically there. So now we are really in the position where we can compare these two approaches. So similarly to the Drinfeld-Kohno theorem, we now have two nice pictures. One in terms of generators, this Lester, Pope ideals. The other one in terms of this monodromies of KZ equations. And yeah, by the way, how these ribbon braids look like. Similarly to the original situation of the Young-Baxter equation, the universal I matrix has a rather complicated form. Right? And similarly here, this on the Q side, this ribbon braid has a complicated form. Actually, the good form is not even known, so it's kind of more like the existence result. While on the KZ side, it's the formula is very simple. So this is your ribbon braid. It's a bit more complicated than the situation for the braiding in the Drinfeld category. Remember, that was basically kind of this factor without 2. So here you have extra factors, but still it's a very manageable expression. So now we can compare these two things, and it turns out that they indeed correspond to each other. So this is our main result. So the claim is the following. So you start with any star ideal. And then you consider the ribbon braided modular category of modules over these ideals. It's a modular category or the category of modules over the quantized universal enveloped algebra. So more precisely, you don't want to consider the entire set of all categories because, well, because of that non-simplicity, because of that central element in the Lie algebra, you actually have a lot of bad modules. So you don't want to consider it. So we rather consider a relatively small category generated by just trivial one-dimensional module. Or another way of putting this, we consider only such modules over this algebra which can be embedded into modules over this algebra. So this is what we do kind of on the Q side. And similarly, on the KZ side, we can consider this category of, again, G sigma modules, which we consider as a modular category over the Drinfeld category. Again, we don't consider all possible G sigma modules because there are some really bad ones. So we consider only the ones we can generate from the trivial module, or in other words, the ones which embed into G modules. And with associativity morphism divided by this associators defined by two cyclotomic KZ equations and this ribbon braid, which I wrote here. And the claim is that such things are equivalent under some correspondence between these parameters, T and S. And moreover, going from T to S, you can do it essentially in a unique way if you require just some naturality conditions. So what happens is that if you just look at this algebra and you look at the classical limit, you're actually not going to get a quantized universal enveloping algebra of G sigma, but rather some conjugation of it. So the equivalence of these categories is go as follows. So you can first conjugate so that you really compare with G sigma, and then after this conjugation, you may require that your equivalence is trivial, so the identity one modulo H. And if you do that, so you can see the only equivalence of this form, then this parameter S will actually be uniquely determined. And as a result, then we have this analog of the Kohno-Drinfeld theorem that you have two types of representations of type P braid groups. One defined by this universal K matrices defined by Balagovic for Lefter coideals. On the other hand, you have monodromy representation defined by these two cyclotomic KZ equations. And these two representations are equivalent. So finally, let me say that, yeah, we actually don't know explicit formula for this S in terms of the parameters in general. We have only sort of the initial term S0 for it. So it's more sort of existence result, but the exact formula is not known. But in this maybe most studied, most interesting case, A3 case, we do have a complete formula. So just to get a feeling what kind of formulas we're talking about, here is this result. So if we consider this A3 case, so a symmetric pair of this form. So again, remember that we have two different cases when P is half of n and when P is less than half. So in the first case, this parameter S is expressed as follows in terms of these parameters defining coideals. In the second case, this parameter is expressed by this easy expression, again, where this is one of the parameters defining the coideal. Okay, yeah, I finish at this point.
Yeah, so thank you very much for the nice talk. And I invite questions from the audience first, and then online questions if there are any. So if no one has a question yet, maybe I can ask a kind of basic question. So this type B braid groups, could you elaborate on like how they are motivated? Why do you look at them? I mean, is there some deeper reason behind it?
Well, I mean, you can associate braid type groups with any Cox-Stecker group. So this is simply one of the ones corresponding to type B. So you really have a family of them. So the group corresponding to the type IN are much better known, but these ones are defined in a similar way. Okay. But you have other types as well.
Okay, because I was wondering.
But from the point of view, if you want physics application, as I said, they appear in the study of this quantum scattering on the half line rather than on the entire line. So we can put a wall in the middle, and then sort of the bounce of this wall. And so you need this extra operator corresponding to this bounce, and this leads to this type P braid groups rather than the usual braid groups.
Okay, thanks. Are there further questions? If not at the moment, let me have a look if there's anything online. That doesn't look to be the case at the moment. So yeah, I think we can thank the speaker again. And we will resume at 50, I think. We will resume at 3:50, I think. There's a coffee break now.